So the first speaker of today is Roman, and he will tell us something on observing and modeling the dust and gas of the most luminous galaxy known. So please, Roman, the floor is yours.
Thank you, Claudia.
I will give you a 3-minute reminder.
Okay, perfect. And I guess you can hear me and you can see my screen? Okay, perfect. So yes, well, first of all, I'm going to introduce myself. I'm a third-year PhD student in the University of Crete, and I'm right now undergoing a studentship in the European Southern Observatory. And yes, I'm going to talk, as Claudia said, about the observations with ALMA and the modeling of gas and dust of the most luminous galaxy known. So first, I want to introduce hot dust obscure galaxies. So this type of galaxies are were first detected with WISE, and they were selected to be undetected or very faint in the short wavelengths. I don't know if you can see my mouse, of 3.4 and 4.6 bands of WISE, but well detected or very bright in the 12 and 22 microns. So this means that we are targeting very obscure but very luminous objects. And we found that, well, first of all, this type of galaxies are all located above redshift 1, so high redshift galaxies, and they have some interesting properties. So first, very high luminosities. Most of these hot dust obscure galaxies or short hot dogs, they have volumetric luminosities above 10 to the 13. And in some cases, especially for the high redshift range, above 10 to the 14th solar luminosity. So we are really seeing the most luminous objects in the universe. They also are powered by AGN. So we look at the SEDs. Here you can see in the right some templates of different type of quasars and just an AGN with hot dust component. And that's how most of the hyperluminous hot dogs looks like. So completely AGN dominated SEDs. They are also accreting at the limit, so we are not in a equilibrium phase. This is just, well, we have Eddington ratios close or above unity, which means we have a very intense accretion and very unstable phase. And this is also related with the fact that we see high turbulent gas with C+ observations of hot dogs. And also there's detections of high velocity gas outflows in the optical. So this is all related with the fact that we are accreting at the limit of the stable accretion. And then if we put these hot dogs in the context of how we believe galaxies evolve, especially in a merging-driven scenario. So we have hot dogs normally are in overdensity environments and undergoing mergers. They are very obscure, so we believe we are looking at a phase in which, the very luminous quasar it's on the way to unveil an optical quasar to blow up the gas and the dust. But we also believe this is not just a single phase; it's just something that will happen many times, recurrent times, in short phases, and will eventually unveil the optical quasar. So now I'm going to focus, which is what my research is focused on, one specific hot dog, which is this one, and for short, I'm going to call it MAYA2023, which is the most luminous galaxy known, and it looks like this. It's a merging system. We have a host galaxy in the center and at least 3 galaxy companions. And all this merging system is connected by, we are here looking at the continuum observations with ALMA. So everything is connected with dust tidal streamers. So it's a complicated and multiple merger system. And then some properties of the host galaxy, we focus on the host galaxy, and it's located at redshift 4.6. We have 3.6 times 10 to the 14th solar luminosities, which is what makes it the most luminous galaxy known so far. There are observations of wide, broad optical lines in which we can derive the black hole mass, which is 4 times 10 to the 9. So we have a massive, supermassive black hole in the center. And with these two quantities, we can have the Eddington ratio, and we are quite above the unity. So again, we are in this unstable, violent accretion and outflow phase. And then the molecular mass, molecular gas mass, and stellar mass are in the order of 10 to the 11th. So we are in general, we have massive galaxy, high redshift, and very high luminosities. So now this project is focused on a data set of observations with ALMA. Well, it's a combination that this galaxy is very bright, and also it's located in a redshift in which we can target a lot of different far-infrared fine structure lines that trace all the different phases of the ISM. So it's a very good galaxy as an example of, well, trying to understand how all the phases look in hot dust obscure galaxies. So very briefly, we targeted 3 lines that trace the ionized gas. So we have nitrogen 2, 122 and 205 micron, and oxygen 388 micron lines. Then we have also lines that trace the neutral gas, so the 2 neutral oxygen lines and 2 neutral carbon lines. We have also C+, which comes from both the ionized and neutral phase, but it's mostly arising from photodissociation regions. And finally, we have 2 high transition CO lines, which are coming from the, well, deeper in the cloud from the molecular cloud. I'm not gonna go into details because I don't have a lot of time, but this is just for you to see how each of these lines look, and that most of them are not resolved. With some exceptions, like for example, you can see down here in the left C+, that we resolved at least one of the companions that I was showing before in the dust emission. But in general, most of the lines are not resolved. So we are looking at the host galaxy for you to have an idea of the scale. Here at redshift 4.6, 1 Earth second, it's broadly 7 kiloparsec. So we're really just integrating the host galaxy. And we have also 2 non-detections. So the carbon 609 and oxygen 388 microns are non-detected. And if you are interested, I can go back to this later. Also, I'm not going to go into details, but this is how all the spectra look for each of the lines. Some of them are very well detected and some more noisy. And well, we have I'm going to mention that the oxygen 145, we had a very bright atmospheric line very close to the line, but still we are confident about the detection, as I was also showing before in the moment zero map. And again, the non-detections of neutral carbon 609 and oxygen 3 lines. So now, having this, we have the observations of the line, we have the line ratios, and we can model the ISM. So for that, we use the photoionization code Cloudy. We are trying to model a cloud of gas and an ionization source, which in this case we suppose is just an AGN. So, okay, I'm going to go one by one for all the parameters that we modeled. This was an iterative process in which we were trying to look for the parameters that were more important in the modeling of the gas and of the AGN. So here, where in the left, you can see a corner plot of the parameters and the posterior distributions. So, okay, one by one, first, the best model that we're finding predicts half solar metallicities, which is in the range that we could expect from other AGNs. It's nothing special. Alpha OX, is the ratio between X-ray and optical emission for the AGN. And even if in the literature, we can find it's a broad range between -2.0 and -0.8. Here, less negative means more intense X-ray emission. And we are finding, we are in the range, but we are finding intense X-ray emission, right? Typically, AGNs will have -1.4. Actually, if you look at the posteriors, like this is it's a lower limit. Alpha X is not constrained by our models. So we have, for sure, we need intense X-ray emission to reproduce the line ratios that we are observing. Also, we find, we also take into account the ionization parameter, which is basically the flux density of ionizing photons that your cloud is receiving. And again, well, we find a broad range in other works that were modeled in AGNs, but we are also, well, we need intense ionization to reproduce the observations. And regarding the cloud of gas, we are finding very high densities, so around 3,000 cubic centimeters, and very high extinctions, even above the AV of 300, which is broadly 10 to the 24 in column density. Just for you to see how it compares, how we can compare this best model with the observations. So here you are looking at different line ratios, all well, line ratios with C+, comparing the best model and the observations. And well, you can see that they agree pretty well. This is the best model. We made a very big grid of cloudy models, and this is the best we can find. So the conclusions of this, first of all, we are finding, well, very high densities, as I said, and very high extinctions. We're finding very high X-ray emission. But now, okay, I'm going to try to put our interpretation of how this looks, because, well, we need intense X-ray emission to reproduce the line ratios. We have observations with XMM of this galaxy, and we don't detect the X-rays. So we are finding the model predicts 4 times more X-ray than the upper limit we are observing. So we're not that far, but it's a factor of 4. And also, in all this modeling, we were not including the CO lines because it's high transitions that are not that easy to model with cloudy. But if we try to include them, the modeling it doesn't work, and it's because basically our best model predicts that we don't have, because of the high ionization and the high X-ray emission, we don't have a molecular phase. So, well, taking into account that we're trying to model a whole galaxy, like more than 8 kiloparsecs, which is one cloud of gas, our interpretation of how we can match we need X-ray emission, but we don't see them, and we don't predict CO, but we are observing it, is that we are modeling one of the phases of the gas of the galaxy, but we have another phase that we are not able to model. And it's where the molecular gas is located. It's located further from the central source. Yep. Thank you. And this phase that we are not modeling is both, well, harboring the CO, but also obscuring the X-ray emission. So, well, our plan is we're going to ask for deeper X-ray observations to try to really have a detection of this, and also to have deep CO observations with ALMA to try to see if we detect this more extended CO emission, and we can close this picture, this interpretation that we have for this source. So I think I may have run a bit. This is my gigantic email if you are interested in this, and if you have any question, I'm happy to solve them.
Thanks a lot, Roman. Very nice talk. We already have a question in the chat. You may want to read it.
Yes, so Abhijit is asking for the alpha OX modeling, were you using the observed X-ray emission or intrinsic emission after correcting for the high NH? Okay, so for the alpha OX, we were not varying the X-rays that we were observing. But we found that in order to reproduce the line ratios, we needed to include this more intense X-ray. So we are not using the upper limit detection in the modeling, or not even what we are using to compare with the observations is what you say, like the intrinsic emission after, like because also this is also an output of cloudy. We have the emission of the X-rays, and we have what we would observe through the cloud. And that's what we are using to compare with the observations. And we find that, well, it's 4 times higher than the upper limit that we have.
Okay. Thanks a lot, Roman. So, Sebastian, do you want to ask your question?
Quirino first.
Sorry.
Quirino first. Huh?
Okay, Quirino, please.
Thank you. Regarding the maps that you showed before, the sources that you said that they're not resolved, right? So I have a quick curiosity. Did you try to fit the sources in the visibility space, in the UV plane with the Gaussian,
Yes.
for example? Okay, so you cannot resolve them also in that case.
Yes, exactly. We have, I'm not showing here, but we're also working on the continuum, undergoing continuum of all these lines. And in the continuum, we do see more extended emission. So we could potentially in the future also try to,
yeah, because if you have the sizes of that, you can provide an independent estimate of the density of the column density of
exactly.
given geometry. So it would be helpful.
Yes, exactly. No, for now, this is all just integrated emission. So we're not trying to model any extension. Thank you.
Okay, now Sebastian, do you want to ask your question now?
Oh yes, wonderful. Very great talk. I had a question about cloudy, and when you fit, do you use only the atomic lines, or also does it take into account the CO lines that you have?
So we
to finish the question, the atomic lines, would they trace the same gas component as the molecular lines or not?
So not really. Like we expect CO to be deeper embedded in the cloud. So yeah, first we were not including the CO lines because they are high transitions, and in principle it's not that easy to model this. But as I said, like if we include them in the modeling, it completely changes the results. So that's why, and also if we look at the best model that we're finding, and we can look at the emission of each of the lines through the cloud, and we don't detect the molecular gas. So even if we have neutral gas, but the molecular phase is non-existent, probably because of this high X-ray, high ionization. So that's why our interpretation of, okay, then we should have another component of gas further. So it's not that affected for the X-rays, but it's harboring both the CO and obscuring what the X-rays that we're supposedly non-detection.
Great. We have time for another quick question. So please go on.
Hi. I was wondering about the Eddington ratio that you mentioned. It's, I think, about like 2.8.
Yes.
What method did you use for calculation for that? And sort of like, is it a true super Eddington accretion source, or is it something that has a high error bar that it can be slightly sub Eddington, but because of the ratios that you get?
So yeah, I don't have the error bars of this Eddington ratio, but it's based on these two other measurements. So the volumetric luminosity, it's pretty conservative in principle, the estimation from the SED. So I'm pretty confident this is all derived. And the black hole mass, even if it has big errors, and this is based on I think it's magnesium 2 and carbon 4 optical lines, broad lines. But I think it's also, at least the range, we are for sure over the Eddington, the unity of Eddington ratio, yes.
Okay, yeah, that will make it a really nice source to study, especially that you are essentially, from what I understand, you are seeing sort of a live feedback mechanism happening where the molecular gas is sort of pushed out, and
yeah,
this is really nice. Yeah, great work. Thanks.
Thank you.
So let's thank again Roman for his nice talk and all the nice things